Hello everybody, this is the first video associated with Chapter 6 of the Reinforcement Learning course. So the purpose of this chapter is to introduce a family of procedures called Temporal Difference Learning Methods, which combine ideas from both Monte Carlo reinforcement learning methods we've seen in the previous chapter and um, dynamic programming approaches we discussed in chapter 4. Okay, so we will combine these ideas to derive new algorithms which can have desirable properties. Okay, so this chapter covers material from chapter 6 of the Sutton and Bartow textbook. Okay, so like we said, temporal difference methods, often denoted by TD, so TD stands for temporal difference, they combine ideas of Monte Carlo algorithms and dynamic programming algorithms. Okay, so like Monte Carlo, TD methods, they can directly learn from raw experience without relying on a model of the environment. Okay, so we said that dynamic programming can only be applied if you know that transition function P, whereas in practice often you don't. So TD methods again don't require to know this function to be applied, which is great news because in practice it, it's often a no. Okay, however, uh, like dynamic programming, the temporal difference methods, they update estimates of the value function based on other learned estimates without waiting for a final outcome. Okay, so we'll make that more precise, but if we recall from chapter 4, our algorithm to learn the value function entailed plugging our current estimate of the value function into the Bellman equation to obtain a new estimate of the value function. And this approach will also be used in the temporal difference learning method. We're going to see that more precisely shortly. Okay, so now we're going to consider some notation, some convention to denote the sequence of states. Okay, so again, we will often use episodic tasks. So if we have continuing tasks, this problem doesn't arise. But if you have episodic tasks, then what's going to happen is every episode ends at some point. So what we will do to denote the various states across the various episodes, we'll stack the episodes one at the end of the others. Okay, so for example, let's say for the first episode we have, okay, so T1 here, capital T1 denotes the number of time points in the first episode. So if we have S1 until ST1, then for what we will do is for the second episode, we'll denote the states as successors of states from the first episode. Okay, so ST1 plus 1 is the first state of the second episode until ST1 plus ST2, which is the last state of the episode, and etc. Okay, maybe this notation seems abstract to you, but the next example should make it very clear. Okay, so let's proceed to the example. So we said, well, first, before showing the example, we said we're going to stack episodes one at the end of the other to denote the sequence of states, but this also holds for actions and rewards. Okay, so for example, if we have a realization of 3 episodes of a Markov decision problem and that we have the following states. So episode 1 goes through state A, B, E. So E is the terminal state. Second episode contains states C, E. Third episode contains the sequence of state A, D, B, E. then what we will do is we'll consider the following sequence of states. Okay, so we'll use states of the first episode, states of the second episode, states of the third episode, and we'll stack one at the end of the other. Okay, so if we denote S8, S8 stands for so 1, 2, 3, 4, 5, 6, 7, 8. So the eighth state of the sequence will be B. Okay, so why do we do that? It's just gonna make uh, notation much more convenient. Okay, so when we stack them into all episodes in one sequence, we don't have to introduce an additional notation to represent the episode, which would make things quite annoying in the notation. So this is why we stack the episodes like this. Okay, so this makes the notation more convenient. Okay, so here, recall that T1 is the number of states in episode 1, T2 is the number of states. So when I say number of states, I mean number of time points before reaching the terminal states in episode 2. Ti denotes the number of time points or before reaching the final state in episode I. So here we'll denote by tau, not tau, sorry, T tilde I being the sum of the first T, so T1 until capital Ti, which is the cumulative time across all episodes at which the ith episode ends. Okay, so here, let's say if we go back to our previous example, we had, okay, so let's go here, an episode of length 3, 2, and 4. So here, we in the previous example, we would have T1 is equal to, it was 3 to 4, yeah, so 3, T2 would be equal to 2, T3 is equal to 4. Okay, so here, if we do sum these 3 times, it means the cumulative time at which the third episode ends is 3 plus 2 plus 4, which is 9 here. Okay, so this is the notation which we will use to denote the time at which the third episode ends if we stack all the episodes one at the end of the other. Okay. Okay. Now, based on the same convention of stacking episodes one at the end of the other, tau is will denote the first time s is visited in episode I. And this time here is the time within the long sequence of states where all episodes are concatenated. GT is the return at time t for the current episode. Okay, so GT will be RT plus 1 plus gamma RT plus 2 until gamma times, this is the number of periods between time t and the end of the current episode. So the end of the if, so here we're going to assume if t is in episode I, then this this tau here will be tau I, not tau, but t tilde t. This tilde t will be tilde ti. So this is the time at the last time step in the episode minus the current step times the terminal reward. Okay, so here GT still stands for the return, but now the way it's defined, it's the sum of all discounted rewards. But except now we won't go until infinity. This sequence will stop at the last reward of the episode. Okay, because if we consider the next reward is associated with the next episode, so we shouldn't count it in the return. Okay, so the return ends when the episode ends. Finally, some other notation. IT denotes the episode in which T occurs. Okay, so in the last example, if we had I8, this would be equal 3 because the eighth state encountered in the previous sequence was associated with the third episode. Okay. So this is the notation. We're gonna use notation convention to make the description of the algorithms more convenient in what follows. Okay. So first we will start with the policy evaluation problem, where we're going to consider a fixed policy pi, and we're going to assume we want to estimate the state value function associated with this policy. Okay, so later on we'll consider action value functions and refinement of the policy, but for now let's consider a fixed policy and assume for that fixed policy we want to estimate its value function. Okay. So, for such purpose, if we compare the Monte Carlo with what we're going to do next, the TD method, we can see that both methods, they use experience to solve the prediction problem. Okay, so what we mean by experience is that we don't use the transition function to consider all possible probabilities of the various outcome. Instead, we just either generate episodes either through a natural process or through simulation, and we use this experience, which is the generated episodes, to form our estimates and solve the prediction problem. However, here is one key features which will differentiate Monte Carlo algorithms and TD learning approaches. It is that Monte Carlo methods, they wait for the full return to be observed to refine estimates of the value function. Okay, and when are the full return observed? It's only at the end of an episode. Okay, so before updating any of the values in our value function for Monte Carlo methods, we have to wait for GT to be observed, and GT is only observed at the end of the episode because GT is the sum of discounted rewards until the end of the episode. Okay, so for example, if you apply a Monte Carlo algorithm to learn how to play chess, you have to wait for the end of the game to improve or to adjust your estimates of your value function. This can be a bit slow in practice, so if your episodes tend to be really long, it might be preferable to have a method where you don't have to wait until the end of the episode before adjusting your estimates. Okay, so this idea to start adjusting your estimates before the end of the episode is one key features of the TD learning methods, and this can significantly improve the learning speed. Okay, so to illustrate that, let's go back a bit to our Monte Carlo method from the last chapter. So here, let's say we have a sequence of value function estimates. So V I plus 1 denotes the value function estimate after I iterations. And here, the iteration corresponds to an episode. Okay, so here, the Monte Carlo algorithm relied on the following recursion. So if a state S was visited during episode I plus 1, then we could increment the value function through the following rule. So we could apply the following update. So the next estimate is the current estimate plus the learning rate times the difference between the gain at the first time the state S was encountered in episode I minus 1 minus the current estimate of the value function. Okay, so this is the first visit approach Monte Carlo algorithm that we discussed in the previous chapter. Okay, so here the gain is calculating at the first time state S was encountered in the episode. Okay, so this is if state S was visited. Of course, if state S was not visited during the episode I plus 1, then the next estimate of the value function for that state would be the same because we have no information on the value of S, so we cannot improve on our current estimates. Okay, and here again, we reiterate that this return here is only known by the end of the episode. It's not known before that. So we have to wait for the end of the episode to increment our estimate. Conversely, TD methods, they don't wait for the end of the episode. They just wait for the end of the current time step before updating the value, estimated value of the states. Okay, so here for TD methods, VTS will denote the estimated value of state S after observing state ST at time t. Okay, so here in the Monte Carlo approach, the index here represented the number of episodes because we only updated estimates after each episodes, but now here T doesn't denote the episode, but rather the time step here, because at every time step we're gonna update our value function. So here we're gonna introduce one TD method, one of the simplest one called TD0. But in subsequent chapters, so for example in chapter 7, we're going to generalize this to other values than 0. So we'll have TD something else, TDN methods. But right now, let's focus on the baseline case, which is called TD0, and which applies the following update rule. Okay. So assuming the current state is not the terminal state, because if you're in the terminal state, you don't have anything to learn, you don't update anything. Okay, so if you're in a state ST, then we'll start with the second line. For all states that are different than ST, you don't increment your value function estimates. Okay, so this means you're only gonna, if you're in state ST at some time point t, you're only gonna adjust your estimate for the current state. And how do you do that? Well, then we're gonna use the following rule. Okay, so the next estimate of the value of the current state ST will be the previous estimate of that state plus a small constant, which is the learning rate, times the next reward plus gamma times the value function at the next state, where here the value function is not the true one because we don't know what the true one is, but rather we replace it with our current estimate of the value function minus the current estimate at the current state. Okay, so we can see that these guys, what are the unknown quantities? Here the unknown quantities at time t are the next reward and the next state. So as soon as you reach time t plus 1, all the unknown quantities are observable. So you can indeed apply this rule and you don't have to wait for the end of the episode to make this increment or this adjustment to your value function. So now the next step is to discuss, well, why does this update rule make sense? Okay, so it looks a bit cryptic now, but let's try to make some sense out of it. Okay, so before we go through a more formal explanation, I just want to point out to the following difference. So if we had a Monte Carlo algorithm, then we would have something of this form here. Okay, so this part would be instead the return, because Monte Carlo algorithms would have that your next estimate is your current one plus gamma times the return minus your current estimate. Okay, but here for TD methods, instead of considering the full return, which we'll only observe at the end, we're going to replace this with the next reward plus gamma times the next value function estimate at the next state, which are observable only. So here GT is observable at the end of the episode, but these are observable at time t plus 1. Okay, and one quick rationale to illustrate that, why we can, it makes sense to do some substitution. So recall that the true value function in state t, it is here, it is the expected return, but it's also equal to, so recall that we have gt is rt plus 1 plus gamma gt plus 1, and this guy has expectation equal to v pi st plus 1. Okay, so instead of considering GT here, we're going to consider the next reward plus gamma times the expected value of this new guy. Okay, so this is the idea. And here, this guy here, the true value function, we don't know its value. So instead, we're going to replace it by our current estimate of this value. Okay, so this is an informal justification. It's basically that GT and this guy here do have exactly the same, well, okay, have almost exactly the same expectation, where for both these guys, the expectation would be the value function evaluated at the current step. The one key difference, I said almost exactly the same expectation, it's because for GT, it's indeed the true, the value function is indeed the true expectation, but for this guy, because this is not the true value function, this is only an estimate, then the expectation should be approximately equal to v pi st if this approximation is sufficiently good. Okay. Okay. So we're going to pursue a bit on our explanation. So let's recall from the Bellman equation, which we saw in chapter 4, that the value function of policy pi in state st can be written as the following. So we saw it's the expectation of the next reward plus gamma times the value function at the next time step. Okay, so assuming, so let's write it, assuming that our estimate of the value function at the next state is a good estimate of the true value function, then this implies v pi st is approximately equal to expectation of pi of rt plus 1 plus gamma vt st plus 1 given st. So this is approximate, and on the other side, this is exactly equal to Those, so this is why, because both people have approximately the same expectation, we can take the GT in the Monte Carlo algorithm and replace it by this guy here, which is the next reward plus gamma times the current estimate of the value function at the next time step. Okay, so I'll just erase this. So let's go back to the following rule. So we're gonna pick. So let's go back one slide. We're gonna take this update rule here and we're gonna rewrite it here. So this entails that vt plus 1 st minus vt st. So our increment of the value function is equal to gamma s, not gamma, alpha times rt plus 1 plus gamma vt. So gamma is the discount factor at st plus 1 minus vt st. Okay, so let's read the first point. The current estimate adjustment, so the adjustment is the difference between the next estimate of the current state minus the current estimate of the current state, and this is what's on the left of this equation. Okay, here, so we say it will be an average positive if the estimate of the value function in the current state is smaller than the true value function. And you can invert the words here, so it will be an average negative if the estimate Vt is larger than the true value of V pi. So why is that the case? It's because okay, how to say that? If, okay, so provided this is, as we said, assuming this guy is approximately equal to V pi st plus 1. Okay, so we're gonna disregard this approximation error here, and we're gonna assume that this guy is the true approximately the true value function in the next state. So if we have that, then the estimation of this term, the expected value, sorry, of this term here is V pi st, the true value function at state st. Which means that if the true value function here is larger than this guy, so if this guy is smaller than this, then this in average will be positive, and this means that this in average will also be positive, which means you'll have a tendency to increase the estimated value of your state, which is great, okay, because this says if you're underestimating, if you're currently underestimating your value function, okay, so if this guy is smaller than this guy, where this guy is, okay, sorry, if this guy is smaller than V pi of st, recall that here V pi is the expectation of this guy here. Okay. So if this guy is smaller than V pi, then in average this will be positive, as we said. So this means that if you currently underestimate the value of state st, in average, this will be positive and you will increase its value. Okay, so this is great because when you underestimate the value of st, this algorithm will tend to increase its estimate. And conversely, if you tend to overestimate the value of a state st, then this update rule will tend to decrease its estimate. Okay, so in average, this rule should push your estimate of a state in the right direction. This is again only an average because you have random sampling, but if you face enough episodes, eventually you should push your estimates in the right direction. Okay, so again, one drawback of what we said here is this part here. So we assume that the estimate of the next state is approximately equal to the value, the true value function. So in practice, it might not be the case if you just started doing your estimation, but eventually once you refine your estimates, hopefully this will work. Okay, so does it really work? So is this assumption problematic? This we're gonna discuss in the next course. Okay, so but we're gonna see that it in fact isn't really a problem. Okay, but for this discussion about is this an appropriate assumption, do TD methods converge? We'll have this discussion in the next video. So stay posted about that. One quick detail here. So we said this rule in average pushes our estimates in the right direction, but how fast does it make the pushes? Well, this depends on this parameter alpha here, which is again the learning rate, and which drives the magnitude of adjustments we make. Okay. Okay, so here a bit of terminology. So TD0, it bases its update in part on an existing estimate, VTST plus 1. So if we go back one slide or two slides here, we see that in this part here, which replaced the true return GT, instead of having GT, we use this estimate of the next state. Okay, so when we use GT, so maybe let's write this in Monte Carlo setting. When we use GT, GT did not depend on any estimate of the value function. Okay, so GT is just the return, which is obtained by the actual realized rewards. Okay, so you didn't have to use any inference about this GT. You just take rewards, sum them, discount them, and that's the true value. Conversely, instead of in TD methods, instead of using GT, we use this guy, and this guy, it is an estimate. It's not the true value function, it is your current estimate of the value of the next state. Okay, so because this method relies on estimates of the value of the next state instead of actual rewards, this introduces a bias or some error in the expectation, and we have a terminology in the reinforcement learning jargon to say that relying on estimate for the value of the next state is what we call bootstrapping. Okay, so bootstrapping here in the context of reinforcement learning means that instead of purely using realizations of the rewards, we're gonna use current estimates to quantify the value of the next state. Okay, and this business where we use estimates of the value function of the next state, it's analogous to what we did in chapter 4 when we applied the policy iteration procedure. Okay, so in the policy iteration procedure, uh, okay, so we had something like the next estimate of our current state. Of state S was given. So for deterministic policies, there was one single possible action. So we're just gonna sum here of um, the okay, so this is the next state, reward giving a current action, given current state. And here, if we had a deterministic policy, we don't need to put the action because there's a single possible action in that case. Oops, sorry. So this is not true. Let's consider, instead of having deterministic policy, let's just write the whole thing. A given S of the reward plus VK S prime times, I forgot the discount factor, so here gamma. Okay, so this is the policy iteration procedure we had in the context of dynamic programming, and we see that this method also uses bootstrapping, because here in the right side we also use not the true value function but rather an estimate of it. Okay, so to build new estimates we rely on previous estimates within the update rule. So this policy iteration procedure also uses what we call bootstrapping in the context of reinforcement learning. Okay, so bootstrapping, although when you talk about this in a simulation course, the meaning is slightly different. Okay, so it still relies on some similar concept, but the precise meaning is a bit different. Okay, so let's just say that when we say bootstrapping within the reinforcement learning course, we use it in our context with a precise meaning in our context, which might not be the same than in other statistics class or simulation classes, for example. Okay. Okay. Now, let's introduce a bit of terminology to differentiate the TD, or to do some comparison between the TD updates we've just discussed and the Monte Carlo error updates we saw in chapter 5. Okay, so here we're going to define what we call the Monte Carlo error, the TD error as delta t, and the TD error at time t is defined as the reward plus gamma times the estimated value of the next state. This guy, we're going to call it the target minus the current value, the current estimate of the current state. The current estimate of the value of the current state, sorry. Okay, so what is this guy, this delta t? If we go back a few slides, we see that this delta t is just what's between the brackets here. Okay, so here, this part, we call it the TD error, and we see that the update rule in the TD algorithm is just to say that the increment of our current estimate is alpha times the TD error. Okay, so we can decompose that TD error as what we call the target, which is something whose expectation should roughly be the true value of the current state minus our current estimate of the current state. Okay, so as we said, if Vt was exactly the true value function. So if both this VT and this VT estimates were perfect, then this TD error would have exactly a zero mean because the expectation of this guy and this guy would both be the value function of the current state. Okay, so this defines what we call the TD error. It's the quantity we use to increment our estimates of the value function. And we can also define the Monte Carlo error as the return at time t minus the current estimate of the value function in the current state at time t. And here, instead of being t, I write I of t because it denotes the current episode in which we're in. Because recall that in Monte Carlo methods, estimates are only updated after the episode. Okay, so the index represents the episode number, not the time step number, because we only did increment estimates at the end of the episode. Okay, so recall, why do we call this Monte Carlo error? Recall that in Monte Carlo algorithm, we had something like VI I plus 1. So I plus 1 ST was VI ST plus alpha times G T minus VI. Oops, sorry. VI ST here, something like that, where I is the episode in which time t is. Okay, so we can see that for Monte Carlo algorithm, we still have that the increment of the estimate of the value of a state is alpha times the Monte Carlo error. Okay, so for both the TD error and Monte Carlo errors, the errors are what we use, the quantity we use to increment the value function. Okay, so the increment is alpha times the error of the corresponding algorithm. And again, if VI was exactly the true value function, if our estimate was perfect, then this guy would have a zero expectation also. So this can be seen as an unbiased estimate of the value function given, assuming that our estimate was exactly the true value function. Okay, so as we just showed, for both Monte Carlo methods and TD algorithm methods, the update rule for the value of states looks pretty much like this. The new estimate of the value of a state is the old estimate plus a learning rate times what we call the error. Okay, so we had a different definition for the TD error for the Monte Carlo error. Furthermore, for TD, the estimates were updated at every time step, whereas for Monte Carlo, it's only after the episode. But both have a similar type of structure to update estimated value of states, which is something like this formula. And we're going to see in subsequent chapters, we're going to still use similar update rules. So for many reinforcement learning algorithms, they can be understood as update rules of this form for the value of states. What's going to change between the various algorithms is how we define the error. Okay, so for various definitions of the error, we can get to different reinforcement learning algorithms, and the difference between several algorithms we're going to see in this chapter and in future ones can be expressed as simply changing the error definition to come up with a new algorithm. Okay, so as we said, a key difference here between the TD method and the Monte Carlo method is that for the TD method, if we're at time t, the error becomes observable, at time t plus 1. So you only need to wait for one time step before being able to do the update. Whereas for a Monte Carlo approach, the error is only observable at the end of the episode, which means that you have to wait for the end of the episode to increment the value of the states. Now, one might ask, is there a relationship between errors of the Monte Carlo approach and of the TD approach? And the answer is yes, there's a relationship between them, or at least an approximate one, and this identity can play a very important role to describe the relationship between various reinforcement learning algorithms. Okay, so we're going to study this relationship next. Okay, so here, the relationship we're going to show between the TD error and Monte Carlo, it's only approximate. And the approximation we're going to make is that the values of the states are not updated before the end of the episode. This we just said it's not true. Okay, so for TD learning methods, at every time step, there are updates, so we don't wait for the end of the episode to update the value of states, but just for the sake of comparison, we're just gonna make this approximation here. And in practice, some people might argue this approximation is good because if alpha is sufficiently small, the updates on every episode are not very large, so this could be a very decent approximation. Okay, so we're gonna approximate that within an episode, estimates of values don't change, so the estimate of the value of state stj after time step t plus j is exactly the same that the estimate of this same state after team's time steps, where j is any value between 0. So here, if j is 0, this is exactly time t. And so this is the number of steps remaining before the end of the episode. So this rule just means that the estimates of the value of the various states are not updated within an episode. Then let's try to show a relationship between the Monte Carlo error and the TD errors. So here the Monte Carlo error, it's the return at time t minus the current estimate of the value function and the current state at time t. So here we said that, well, we had in the previous chapter that the current return is the next reward plus the discount factor times the next return. Okay. So this is a relationship we've discussed in previous slides and previous chapters, sorry. So here this minus VT is carried here. And then what we're going to do, we're going to add and subtract the same term here so that the sum is 0. Okay, so here we're going to add gamma VT ST plus 1 minus gamma. So here this is VT plus 1, ST plus 1. So you might say, okay, there's a difference. Here it's VT, here it's VT plus 1. But if we make our first assumption here that the value of the estimate of the next state doesn't change throughout the episode, then these two guys become equal. So this difference becomes 0 if we make this assumption here. Okay, so here, what happens here? So here, if we have RT plus 1 plus gamma VT plus 1, VT ST plus 1 minus VT ST. So here, let's denote it. If we add this guy, and this guy, this is the TD error at time t. Okay, so recall the TD error is this, this plus this, which is a like something whose approximate expectation is the value function minus our current estimate. Okay, so here these three terms, they represent the TD error at time t. And here plus, so here we can combine these two terms here. So this is, we can factor out the discount factor, and this becomes GT plus 1, the return at the next time step, minus the estimate at the next time step of the next state. Okay, so here we have that the Monte Carlo error in one at time t is the TD error plus gamma times the Monte Carlo error at the next step. So we can apply that recursively, and so the Monte Carlo error at the next step, it will be the TD error plus gamma times the Monte Carlo error in two steps. And we can continue like that, apply this rule recursively. So eventually, if we apply it enough times so as to reach the end of the episode, then we have that the Monte Carlo error at time t is the TD error at time t plus gamma times the TD error at time t plus 1 plus gamma times the TD error at time t plus 2, etc. until gamma times, this is the number of time steps before the end of the episode, times the return at the end of the episode minus the estimated value function in the state at the end of the episode. And here both of these guys are 0. Okay, so when you reach the end of the episode, you're in the terminal state, so you won't have any returns, and you know that the true value function in the terminal state is also 0 because you're certain not to get returns. Okay, so this last term vanishes here, so we can express here this summation as the following. So it's the sum for k goes from small t to t tilde it. So this is the time at which the current episode ends minus 1 of this thing. Okay, so the TD error times the discount factor. So this is great. This illustrates the relationship between the Monte Carlo error, which is that the Monte Carlo error at a time step is just the sum of discounted TD errors at each of the steps. Okay, so this just let's have an intuitive explanation of how can this help us to understand the difference between Monte Carlo schemes and TD error schemes. So here, this says that when we do a Monte Carlo update, we consider this whole term here, but when we do a TD update, instead of considering this whole summation here, we only consider the first term of this summation. Okay, so when k is equal to t, we get the TD error. So it's as if when we apply the TD approach, we only consider the very first subportion of the Monte Carlo error to apply the update. Okay, so this draws a relationship between update rules of Monte Carlo and TD methods. Now, okay, so this was useful in itself for an explanation, but this has particular implications when we study what we call eligibility traces approaches. Unfortunately, we won't have to cover these eligibility traces in detail in the current course because we won't have time. However, I'm going to share some material to discuss them a bit for those who are interested to learn more about these. And conversely, in the textbook, there's some material about this. So if you plan to do some reinforcement learning in your career or whatever, just for fun even, and you're interested in finding more performant algorithms, then you might want to look at these eligibility traces approach. So just again, a little digression. Here in TD methods, every time we say at every time step, we update the value of the current state. But here this entails that at every time step, you only increment the value of one state at a time. So the idea behind eligibility trace is that at every time step, instead of incrementing the value of a single state, you can adjust the value of many, many states at a time. Okay, so all states that you faced previously in the episode. Okay, but we won't, for now, let's forget about eligibility traces. Let's just say the following. So eligibility traces allow you to update the value of many states at a given time step, and for this reason, they allow learning faster, and they're very good methods. But we won't have time to cover them in depth, so for the sake of the class, we'll only consider TD approaches. Okay, so this is not in the slide, this is a digression, but I guess this is my plus value in comparison to only reading the slides. Okay, so as we said, the previous relationship between the Monte Carlo error and the TD errors is only approximately valid because in practice, throughout an episode, if you apply a TD approach, then you're going to update the value, your estimate value of the various states. Okay, so in this case, this breaks our assumption one from the last step, but if the learning rate is quite small, updates within an episode are not very large, so the previous approximation is a good one. Okay, so note that conversely, if we consider Monte Carlo algorithms, then the relationship between the Monte Carlo error and TD errors outlined previously is exact. Okay, so now one last item to be discussed before the end of the video is the pros and cons of using a TD method versus dynamic programming or Monte Carlo algorithms. Okay, so as we said earlier, both temporal difference methods and Monte Carlo methods, they have an advantage over dynamic programming for many problems is that they don't require having a model of the environment, and by a model I mean knowing the transition probabilities. Okay, so this is a significant advantage of temporal difference methods and Monte Carlo methods over dynamic programming. So this is one advantage. Second advantage, this is not written here, but the dynamic programming algorithms, they involve very large sums over all possible successor states S prime. So these, for many very large problems, they're not feasible. And moreover, we have another comparison point. So here, instead of comparing to dynamic programming, if we compare temporal difference methods to Monte Carlo methods, as we said, for TD methods, the advantage is that you can update the estimated value of the various states at every time step instead of waiting for the end of the episodes. So this can be very critical and significantly improve learning speeds for applications where the episodes, so here I wrote periods, but I should have perhaps I've written episodes. So if episodes are very long, then waiting for the end of the episode before learning or adjusting the estimated value of states can be very unfavorable, okay? Because it would take too much time before learning and improving. So this TD algorithm methods, they allow circumventing this problem. So even when episodes are long, you can still learn throughout the episode at every time step within. Okay. And this is also this increase in learning time can be very critical if we consider, for example, some off policy Monte Carlo methods that we've uh, seen in the previous chapter. Okay, so if we go back at the end of chapter 5, we presented an off policy Monte Carlo approach, which only learned from the tail of the episodes. Okay, so whenever, as soon as one non greedy action was selected, then we had a loop that did break, and this prevented from learning for all states prior to this breaking point. So a lot of states were simulated in a useless manner, and this slowed down learning very much. Okay, so in that case, the TD learning method, it's not susceptible to these kind of problems. Okay, it learns much faster. Now let me just reread that slowly. Okay, so yes, this is exactly what we just said. So we said that in the previous algorithm there was a breakpoint in which you don't learn from your episodes for all states before that breakpoint. Whereas if you apply TD learning, you're not uh, constrained by this breaking point. You're gonna learn from all states of the episode. Okay, regardless what actions are taken, even if it's the non-greedy one. Okay, so this is another advantage of TD learning methods, which shall increase learning speed. Okay, so we'll stop there for today. On the next class, the first topic we're going to discuss is the convergence of TD methods. So earlier today, we mentioned that we had to make some approximation here of the value function of the next state by its current estimate. And we said, is this approximation sound in practice? Do we still have convergence? So this is going to be the first point discussed in the next class. All right, have a nice day.